Welcome to Friday, guys. I hope the substitute's playing you some rock and roll music. Highly doubt it, though. But today, a quick set of notes. I just want to run you guys through how to convert what is called an octal number to a decimal number. Very similar to binary. You could think the preface of the word is kind of how many digits we're working with. So binary was 2, octal, octagon. We're going to actually start working in the base 8 system. And the big thing about this is that I know we've only talked about decimal and binary, but we can honestly use any base that we want to represent a number. Octal is what we would call base 8. We will run into something a little bit later called hexadecimal, which is base 16. You might be thinking, why would we ever use that? There are some very useful things that we can utilize that for. But basically, any positive number greater than 1, so you can't have a base 0, for instance, you are able to find any base system you can to represent that particular number. Again, the reason why, there are lots of reasons. And for computer science, we'll find that hexadecimal works very conveniently with binary when we get to that section. So let's talk about octal really quickly. Look at this digit that we have here. This number is 270. Now, this is a base 8 number, so most people would look at this and read it as 270. Not today, ladies and gentlemen. But the big thing I want to start with octal is remembering that when we work with a base system, we're really saying this is how many digits I have to represent in a single placeholder. When we are using octal, they're saying you have only 8 numbers you can use. The number one misconception people think is that those numbers are 1 through 8. The 8 digits that we actually want start at 0. So we get the numbers 0 through 8. Misspoke there. 0 through 7. Those are the digits that we have. So the largest number you can place in a single placeholder for octal, 7. Let's take a look at how we work this, though. It's going to be exactly the same as we did before. We're going to split each individual number into its own little problem. And notice that when we use this, it is the base raised to the 0 power for the very first placeholder's value, 8 raised to the first power, 8 to the second power, and we would keep going so on and so forth from there. So we just calculate this out. Anything to the 0 power is 1. 8 to the first is 8. 8 squared is 64. So we run through, we grab our digits, multiply them by the value of those particular placeholders, add them all together. Ladies and gentlemen, did you know that the number 270 in base 8 is actually the number 184? You can see how this process is almost identical to what we have done with our binary to decimal conversion. The only thing that has changed is the actual base value that we use in the calculation. These 8s used to be 2s back when we did binary. Let's look at another example really fast. This, I want you to start recognizing some small aspects of this. This is like us in the decimal world writing the largest possible 3-digit number we can. In decimal, we can use 10 characters, 10 numbers, the largest being a 9. So we could write the largest 3-digit number in decimal as 999. But in octal, the largest digit we get to use is a 7. So unfortunately, the largest number is 777 as a 3-digit number. Identical process once again. Calculate your indices values. This is 8 to the 0, 8 to the first, 8 squared. Or if we did that math, that is a value of 1, 8, and 64. We will then sum those values together. Again, you might need a calculator for a few of these, but if these were ever on an assessment, we actually are very nice to you guys. You end up with a value that is 511 in the base 10 system. Something to keep in mind. What number would come after this? What is the next largest number? If I wanted to represent the number 512 in base 10, this is very similar to, well, what happens after the number 999 in the decimal world? All those 9s roll over to a 0, and we add a fourth digit that goes to a 1. So it becomes the number 1,000. What's actually kind of weird, the next number after this, all these 7s would flip to 0, 0, 0, and we would add a 1 on the left-hand side. It would look like the number 1,000, but it's actually the number 1000 in base 8. Kind of a cool concept that we look at. And look at that, I got ahead of myself jumping into it. Exactly what I had mentioned in that previous slide just kind of shows up right here for you guys. I would like you guys to pause this really quickly. Try to convert this value. It looks like 10,000, but again, this is 10,000 in base 8. Please take note. You will have to calculate 8 to the 0, 8 to the first, 8 squared, 8 cubed, and 8 to the fourth. I don't know about you guys. I don't know those off the top of my head. Please use a calculator for this. This is one where I'm just testing your ability to see if you guys can handle the big numbers or not. Pause now. Welcome back. Let's look at how this one turned out. Again, break up all your digits. 8 to the 0, 8 to the first, second, third, fourth. Take your digits individually, attach them to the multipliers. We find out that, congratulations, you multiply them all together, you get 4,096 in base 10. If you had trouble with this, remember, just ask a neighbor, work together for you guys. Make sure you guys can all understand this. Last example that I wanted to go through is octal in bits. How many bits are needed to store a single octal digit? I want you to think of this as the process of, well, a single octal digit is the numbers 0 to 7. So 7 is the largest possible number I would need represented in the octal world. I am basically asking how many zeros and ones in binary would need to be used to store 7 unique items. This is the equation that we often look at as 2 to the x power is how many unique numbers you can create. Well, if I'm looking at the numbers 0 through 7, I know that 2 to the third power is 8, which means I can create 8 or store 8 different numbers in 3 binary digits. So it would only take 3 zeros and ones to actually get that going. Here's what I want you guys to think about for your program. You guys, after today, or starting today, I should say, are going to be taking your programs, adding another functionality to it. In your drop-down menu, you guys are going to be adding an octal to decimal conversion. The process you are going to use, and I want to see how far you get on your own here. You are going to need to add the additional option to the drop-down menu. You are going to need to, in the convert function, add another statement, something like else if my selected drop-down item is base 8 to base 10. So you're testing for 2 different drop-down menu items now. And you're also going to have to make a new function, probably called oct2 des. And that is going to be your octal to decimal converter. Parameters, well, in order to convert an octal number to a decimal number, they probably have to give you an octal number. I want to highly suggest this. I'm going to point one thing out in particular. You really want to utilize your binary to decimal function. The only thing that you are realistically changing is a couple of names, because you're not working with binary numbers or binary arrays anymore, but rather octal numbers and octal arrays. But the second and most important thing that has to change when you're doing your calculations and you're using the 2 to the ith power, that was because we were in base 2. If we are now doing this to base 8 numbers, I would think that that has to be 8 to the ith value. That's my huge hint for you guys. Again, utilize each other, going back and forth, bouncing ideas off of each other. I will be back on Monday. You guys enjoy your wonderful weekend and take care, ladies and gentlemen.